All right, thank you for the introduction. So we had already 2 talks on this topic on like graph neural networks and deep learning on graphs. And I thought I'd make this talk as a bit of like a tutorial talk in the beginning and then dive into one more project at the end. And the talk is going to focus mostly on unsupervised methods for learning on graphs. This is in collaboration with a couple of people from University of Amsterdam, the Amsterdam Machine Learning Lab, but also University of Toronto and University of Edinburgh. And to start, so we know we have lots of like graph data sets in the wild, but there's also another motivation for why learning with graph structured data is important, because if you look at the world around you, you see a lot of implicit structure in your environment. If you look at this image here of a traffic scene, you immediately recognize there's cars, like different objects, they have different relations between them, like one car is in front of another car, and these kinds of entities and how they behave that dictates us or that tells us how this kind of model evolves in the future. Like, you can easily imagine how like the next few time steps in this image would look like. Similarly, if you look at this picture here, you have a sports scene where everyone is fixated on this ball. So you have like you easily recognize different objects or different people and how they relate to each other. Or similarly, if you try to understand what is going on here, there's many like Lego blocks, and you can think of like how to basically put them together, and you easily understand the relations between things. So this kind of world understanding in terms of objects and their relations is a very kind of useful way of abstracting things for learning. Now, this doesn't end here, so we also have like a lot of explicitly graph structured data in the wild. If you look around you, then there's like social networks, citation networks, or the World Wide Web. It also in sciences, you have like molecules you can represent as graphs, biological networks, or also what's relevant for industry is like representing knowledge in a graph structured format where you have attributed edge types, like how one person relates to another entity in a knowledge graph, for example, or something like roadmaps. And what got a lot of this research started is basically that when you look at these data sets, you realize that the standard deep learning toolbox, like convolutional neural nets and recurrent neural nets, they don't really work here. So of course you could do like a convolutional neural net on this like map here, but at the same time it doesn't really have the right inductive biases for learning very effectively, like what does it mean if a car moves along a certain street and so forth. And in this talk, I'm going to start with a little bit of background on different variants of graph neural networks and their trade-offs if you want to use them in practice. And then I'm going to focus on graph neural networks for unsupervised learning with explicitly graph structured data. So let's say you're given a graph and you want to learn some representations on this graph. And these representations or node embeddings could be useful for link prediction or node classification. And lastly, I'm going to talk about, in relation to this motivation in the beginning, like what happens if you don't really have explicitly graph structured data, but you still want to use the useful inductive bias you get from these models to learn something about relations in some data. For example, you observe some dynamics of some like mystery physical system, and you would like to figure out how things are relating to each other or how things are interacting. And I'm going to conclude in the end. So graph neural networks, the way I usually look at them is you have like a model where the main idea is to pass messages along edges of a graph. And then these messages are basically parameterized by some neural network. And then you have some agglomeration function, and you transform the final output again by a neural network, for example. And all the like notation I'm going to use here is basically we have a graph as like a tuple of vertices and edges. And we represent nodes here by node feature vectors hi, and we represent edges by edge feature vectors hij. So that's basically all you need to know at this point. And I've already seen in the last talk that you can basically put these models like together in like a multi-layer neural net. You have many layers, and you stack them, and in each layer you have these kind of like message passing operations. Now, to start as a motivation for why this like message passing paradigm makes sense and how it relates to things you might already know. If you look at convolutional neural nets on grids or like on images, then you can also see them as a message passing operation. So usually if you look at CNNs, you see them as like sliding a filter over an image, and you take the inner product of this filter, of the filter weights with the image. But equivalently, you can represent the same kind of system as you have each pixel is like a node in this kind of grid graph here, and in order to update the representation of this like middle node here in the next layer, you pass messages from all the neighboring nodes. And you can give all these nodes a name here, and these nodes here could be like RGB values at a certain pixel, or like hidden layer activations at a later layer. And then the whole convolutional update basically looks like this. You have transformations, or you have messages, which are basically the feature vectors at the neighboring nodes, and you take a linear transformation of these feature vectors. And then in the end, you add everything up. And the special thing here is that for each different neighbor relation, like you have an upper left neighbor, you have an upper right neighbor, for each of these relations, you have a different weight matrix. So you have now here going from W0 to W8, and each of these basically is specific to the relation in the image. Now, it's not hard to see how this could be generalized to, say, undirected graphs. So if you have some kind of graph with like a kind of a richer structure, where you don't no longer have like this nice symmetric grid structure. And so one model class that I now here refer to as graph convolutional networks. This is related to earlier work on graph neural networks, which has quite a long history these days. But essentially the model here looks as follows. So you would like to learn a model basically on this undirected graph here, and you want to update for this node in red, you want to calculate the update for the feature vector in the next layer, basically. And again, you can solve this by a message passing function. And if you look back at like what a convolutional neural net on images would do, so the easy way of like generalizing this would basically be to not assume anything about the neighbors. Basically, say every neighbor has the same relation to the node. Basically, it could be the relation could be a friendship relation on Facebook, and then you would assign the same like linear transformation, the same meaning to each neighboring edge. And in this case, all the model would do is basically have like kind of this diffusion or aggregation operation here over these neighbors. So here, these are all the neighboring feature vectors. You transform them all of the same weight matrix, and then you normalize the sum, because if you don't normalize it very often, these things blow up for very large graphs if you have very many neighbors. And gradient descent is not scale invariant, so you really care about the scale of these activations. The only thing that you can really discern is like first order neighbor versus like a self connection that has a kind of a different relation. So you can assign it a different weight matrix, or you cannot. So you can also put them in the same kind of relation type. And this type of model now has weight sharing over all locations. So basically these weight matrices or this update rule is applied in parallel over the whole graph. And it has linear complexity, like you only need to touch every single edge basically once in the graph for this update, or once per direction. And you can also apply the same message update rule in an inductive setting, because with weight sharing, you can basically train this on one part of the graph and apply this once it's trained on like an unseen part of the graph, for example. The only problem is that it doesn't really consider any pairwise interactions, so it really looks at neighbors in isolation, and it pulls the update in, and then it updates the node itself. So it cannot really be sensitive to something like physical dynamics, where you have forces that depend on the distance between two nodes, for example, like inverse square law forces. So this is a limitation of this model, and it also doesn't have any support for edge features. Like if you had different feature representations for edges, like edge types or some richer information, this model would not directly support it. And then at the same time, what I forgot to say is you have this activation function here, and of course this can be anything. This can be like a pointwise activation function. It can also be an MLP itself, so you can basically flexibly choose what you put here. And now if you want to make this model more expressive, there are certain extensions of this basic framework. So essentially they mostly follow this type of rule here. So essentially This is inspired by how like a convolutional neural net would work on images. You basically take each neighbor now has a particular relation, for example, and then you transform each neighbor, if you have some particular relation type for each neighbor, you transform each neighbor according to this relation type, and then you also sum over all the relations in the end. And this is something that basically fits in a framework also called MONAD, or something we've done on what we call relational GCNs for knowledge graphs, where then the edge type dictates basically this relational matrix. And an extension of this framework is basically to not fix this normalization constant. So far I haven't really talked much about this normalization constant. Usually in the early works you would basically just say the normalization constant is something like 1 over the number of neighbors or something that depends on the number of neighbors. But you can also choose this normalization constant here basically based on the features of the neighbors. So you don't have to necessarily take the node degree, but you can also just choose the activation of the neighboring feature vectors. And that's basically what is the basis of self-attention models or transformers in NLP. But also it has also been, basically this model also has been applied to graphs in this paper called Graph Attention Networks. And here, most of the papers roughly follow this kind of rule, that they basically take neighboring features of both nodes, and they do a bilinear product and then a softmax. And this gives them like a learned adjacency matrix in a way. And if you apply this to NLP, then these relation types, like this graph that the model learns, can discover things like semantic relations to some degree. And lastly, a third type of models that has been around for some time now, that people are using in practice in many of these deep learning on graph tasks, is graph neural nets that have explicit edge embeddings. So this is often now known as neural message passing because of this paper here in 2017. But an earlier version already has been published in NIPS 2016. And essentially the main idea here is that you take pairwise interactions into account. So instead of like transforming each neighbor individually and then summing them up, you take a pair of neighbors, you calculate a representation for this pair, and FE here would just be an MLP or neural network, a small neural network. Then you get like high-dimensional representations for the edges. So you basically have like a node-to-edge space update, and then once you're in edge space and have these edge features, you can move back into node space by summing over all the, say, incoming edge features for a particular node and pass them for another MLP. And this type of model now has so these types of models are very powerful in practice. They have explicit support for edge features. They are very flexible, and like you can basically choose any kind of model here. So you have a very flexible and expressive parameterization if you choose so. And you can still support sparse matrix operations. So you can still implement this efficiently with sparse matrix multiplications or with scatter-gather operations on GPU. And the problem with these models is that you need to store intermediate edge-based activations. So for each edge in your graph, you would have to store really a high-dimensional activation vector for backprop later. And this can be very memory intense. So let's say you have 1 million edges, and for each edge you have to store like a 256-dimensional vector. That can be very expensive. And in practice, because in edge space calculating these activations is also much more expensive, so it's significantly slower than these models that operate solely in like the node space, like GCNs. Now, if you now want to use any of these models for, say, supervised or semi-supervised learning on graphs, then you can basically follow a very simple recipe. And this would basically look as follows. So you have a graph as an input. You have node features for each node, which you would summarize here in this H matrix. And then after a couple of these updates, at the end, you basically, so the graph stays the same. And at the end, you would basically get, for every single node, you would get an output feature vector. And then you can put these output features into a node classifier. So you could just basically put a softmax function on top, or softmax classifier on top, and train the whole thing end to end. This is something we've done in a paper called semi-supervised classification with graph convolutional networks a few years ago. And similarly, you can do the same kind of protocol, but use it for graph classification, but then you need to do some kind of aggregation operation. So the naivest one is to just take like a sum pooling over the whole graph, but you can also do like things like attentive pooling or average pooling, and then have like a softmax classifier on the graph level. And lastly, you can also take exactly the same model and use it for link prediction. So you basically would use your final node features, and then you, in order for basically having a link classifier, you have to compare two node embeddings, or you have to have basically define a function that takes two node embeddings as an input. And one of the simplest ones is basically just take an inner product, but you can also, if you want to do directed edges, you can do an MLP here or any kind of more complicated function. And in this simple case, it looks like an autoencoder because you start with like an adjacency matrix and a feature matrix, and then you try to reconstruct the adjacency matrix at the output. So that's a framework. It's also known as graph autoencoders. And so this is kind of just a very quick overview of how you would do supervised or semi-supervised learning in kind of the simplest case with these models. Of course, there are many extensions that you could come up with. And now, like the last point, like graph autoencoders already gives you kind of an idea of how you could use these models for unsupervised learning if you really only care about learning node representations. But you don't really know what the downstream task would be, like if you want to do later link classification or node classification. And so here, what I mean here is basically the objective in this part of the talk will be to learn node embeddings for certain downstream tasks. And most recently published approaches here follow like this kind of modular framework. And in the end, you have sort of a contrastive learning approach. So how this would look like is you start with some kind of graph, then you would encode like nodes in this graph according to either an MLP that only looks at the node itself, or you have some kind of patch encoder that looks at the neighborhood. You embed it into some kind of space. So this representation here you can choose freely. It could be just a Euclidean space. You can embed things on a hypersphere or in a hyperbolic space, or you can represent things as Gaussian distributions as point clouds. So basically, it's only up to your imagination what you put here. And then later, you have to score things. You have to score pairs in this embedding space. Pairs basically should be scored as positive if they're connected in the original graph, and as negative if they're not connected. And the negative component here would basically be sampling. So you would sample some negatives because you usually have like many more negatives than positives. So you would have like a sampling component here that samples some negative examples, and then you score your positives, you score your negatives, and then you feed it into some kind of loss function. And all of these components, basically, you can freely choose. And there are many published like frameworks that use a certain combination of these, basically. So for the sampling strategy, you can, for example, take a positive sample would be just a direct neighbor in the graph. A negative sample would be a random node. Or for different encoder variants, you can use a graph convolution network or something with attention or an MLP, or you can use a lookup table if you don't have any node features, like basically an embedding feature. In terms of node representations, you can change out the geometry of the latent space, or you can use distributional embedding. You can embed things as like Gaussian distributions or point clouds. And you have a lot of like flexibility in also choosing the score functions. Like there's basically a whole literature on these like energy-based or contrastive learning score functions, and you can choose any of these basically. And lastly, with many of these, then you lastly have the choice of a loss function. And here, most people use cross-entropy losses or hinge losses, but there's also other energy-based losses that are very powerful in this case, like square exponential losses. That's a question, yeah.
Sorry. When I think about unsupervised learning, I think of things such as clustering or dimensionality reduction. And so it wasn't clear to me, maybe you can repeat again, how this proposal would support traditional unsupervised learning tasks.
So this is related to things like spectral clustering on graphs. If you would take just a lookup table here, and you would take positive sampling and negative sampling just based on the neighbors and random nodes, then this would be like a sampled version of spectral clustering in this case. So it relates to established methods, but for scalability, you might want to use something like sampling here. So in the end, it's basically a more scalable framework of more traditional methods. Like in traditional methods, we would maybe do, for spectral clustering, you would actually calculate the eigenvectors. And for very large graphs, this can be quite expensive if you want to get like not just a few leading eigenvectors. So that's just an alternative way of looking at these types of models, but a very good question. And so this is a simple table, well, kind of maybe a bit of an overwhelming table of some examples in the literature that fit into this framework. And I don't want to go over all of these, but maybe just to pick out a few of them. So this is graph autoencoder framework, where as an encoder you would use a graph convolutional net, and you would embed things in Euclidean space, and then the score function would just be a dot product between two embeddings. The loss would be binary cross entropy between the positive and the negative score, and you have this simple sampling strategy. Then a recent method called DGI looks very similar. It basically has almost everything the same, apart from this score function here, where they don't score two nodes with each other, but they basically score a node embedding against a global summary, where they basically pool all the node embeddings. And the sampling is now done by having the positive samples are basically given by the original graph, and the negative samples are given by a randomly corrupted graph. And similarly, you have a method here, graph to Gauss, that basically uses an MLP encoder and then embeds things as Gaussian distributions. And the score function is now based on the KL divergence, which defines like an energy, and then they use an energy-based score function. But in the end, you could switch out parts of these frameworks and then compare them against each other. And that's something we've done. It's not published yet, but we have some early takeaways. Essentially, what we found is that graph-based encoders do very often improve performance. Like if you use an MLP versus if you use local patches to encode nodes into the space, then very often sort of a patch encoder wins against simple MLP encoders. And also, neighborhood-based scoring is very effective for link prediction especially, but you can also use it for node classification. Like you can also embed nodes based on this simple link prediction objective for using these node embeddings for downstream tasks like node classification. And another method like this Deep Graph Infomax paper, they do local global scoring, and their method is especially effective for node classification, but the embeddings you learn there are not very useful for link prediction directly, for example. And lastly, the ideal representation here is very highly data dependent. So there's basically no clear winner across data sets. If you take multiple different data sets, and for some data sets like hyperbolic embeddings win, for other data sets hyperspherical embeddings win, for other data sets you might just use a Euclidean embedding, and that's the best representation. And we're gonna soon release a library that is developed by Daniel Daza. It's a master student I'm currently supervising. And he's basically put all of these components together and has a nice benchmark suite where you can basically run all these methods with an automatic hyperparameter optimizer and just see like how different choices compare. And this is going to be released hopefully quite soon. Right, so that basically concludes the part on unsupervised learning with explicitly graph structured data. And I want to just briefly mention a few other applications of graph neural nets. So you can also use this paradigm of like auto-encoding a graph for link prediction for recommender systems, because recommender systems, you can also see them as bipartite graphs. And we had a paper where we essentially just directly take this auto-encoding approach to recommend links. And this can also be extended to very large data sets, this paradigm. If you use a sampling encoder, there's a paper called GraphSage that basically subsamples neighbors in like this GCN framework, and that can basically lead to very large, that can basically help you apply this method to very large data sets. And similarly, it doesn't, since the model doesn't really care too much about what kind of data you apply this to, you can also use this for knowledge base completion, where you can use the same paradigm for link prediction knowledge bases. Or you can use these methods also what we've seen in an earlier talk for semi-supervised learning. Now, to go to the second part of my talk, one recent application I want to highlight for graph neural nets is it's going a bit beyond like explicitly graph structured data. You can also use these methods for problems where you say have an image and you would like to ask certain questions about an image. You would like to understand what's going on in an image. And in this case, if you're given what like the nodes in the graph are, then, for example, to answer this question, are all these animals of the same color, you would have to basically first identify all the sheep and then compare each, like the color of each animal basically to come up with the final answer. And this kind of graph structured representation is also very useful here as sort of an implicit inductive bias to solve these problems. And so in the second part of my talk, in the last few minutes, I want to talk about how to model implicit structure with graph neural networks, and especially with a framework we call neural relational inference, where we try to discover certain interaction types in graphs. And the motivation here is that, let's say we're given some kind of mystical physical system like this one on the left here, and you would like to understand the dynamics of what's going on here. And looking at this might look a bit confusing, but if you highlight the connections between these particles, they're connected by, say, invisible springs, and this gives rise to these interactions and gives rise to the dynamics, then you can better understand what's going on. But our goal is basically to look at the system on the left without revealing what are the actual hidden dynamics between, or hidden interactions between the systems, and try to model this with a graph neural net. And if you try to build a model for this type of data, then classically in a machine, if you look at a machine learning toolbox, what you would do is basically you take all the particles in this case and their trajectories, you would encode them as some kind of feature vectors, you would concatenate all these feature vectors, and then feed them into some MLP or some RNN if you want to model the dynamics. And surprisingly, this already works quite well. But then the problem is once you, let's say you train this model on 5 particles, and now you suddenly get a 6th particle in the box. And you would still like to be able to predict, because the dynamics probably haven't changed too much. But your model is only basically applicable to this particular setting, because you don't really do any parameter sharing. So this is kind of a big problem. And another problem is that the nodes are basically completely arbitrarily ordered if you would like to use something like an MLP. So you need something like permutation invariance in this case, so that you can basically permute the order of the nodes and still be able to predict. And the model also doesn't really know about the structure of the interaction. So in many physical systems, but also real-world systems, you have interactions that are pairwise. So it's a good abstraction to just look at pairwise interactions. And in these cases, graph neural networks are an ideal candidate because they fulfill exactly these points. So they are invariant or even equivariant to permutations in your representation, and also they consider explicitly pairwise interactions. And this has basically led to this development of these interaction networks, or which was later extended to neural message passing for a physical system in a paper by Peter Battaglia. And here we know that using graph neural networks we can model interacting systems with a very high precision if we know about the underlying structure of the interactions and their types. So basically, if we inform the model that all these particles in the string are connected, then this type of model can do really well. But we looked at this and thought, like, okay, what can you do if you don't know these interactions a priori? Can you basically build a model that has like a 2-step training phase, one where it tries to discover what are the actual interactions between like particles in your data, and then predict the future dynamics given this interaction graph that it discovered. And that's a paper we had at ICML last year with Ethan Fataya, who was an equal contributor on this project, and several people from University of Toronto. And here, as I mentioned before, so the idea is basically you would like to learn the dynamics of an interacting system without knowing the structure of these relations, and you would like to infer this latent interaction graph plus maybe even edge types using some kind of autoencode framework. And so we applied this model also for interacting systems, motion capture data, and multi-agent systems, so it's very flexible. The only thing you need is basically fit these assumptions that your data is consistent of multiple objects and you have pairwise interactions. And how the model works is basically, again, an autoencoder that uses graph neural nets, but now turned inside out, essentially. So it's exactly the other way around that the model from the earlier project worked. So here now you essentially have a proposal model that runs a graph neural network on the initial fully connected graph, and you don't know anything about how things are interacting, and it proposes an interaction graph. So basically, you have a model that tries to predict how things are connected, or tries to predict the graph from some non-graph structured data. And so the graph here is represented by this latent variable z, and it essentially tried to build like this variation posterior here, q of z given x, and x is your dynamics data. And then in a decoding step, you essentially run a graph neural network that is now constrained to send messages on this graph. So it cannot send any messages along edges where there was no edge predicted, for example. Or it can only send messages along edges that belong to the certain edge type that the graph neural net is particularly operating on. And then it has to reconstruct the dynamics. So with this autoencoder framework, we can formulate this as a variational autoencoder, which basically, if you're not familiar with this, just means we have a reconstruction objective that tries to encourage the model to reconstruct the original dynamics or predict future dynamics. And we have part of the objective should regularize whatever the latent graph here looks like. So basically, if you already know the graph should be very sparse, you can put a prior on that says, okay, we want to have a sparse graph, and then this term here would basically tell the model to only predict sparse graphs in the latent setting.
So in this case, it's fully connected, the graph?
Yeah, so we start with some proposal here. This proposal can be fully connected, it can be nearest neighbor graph, but you have to start with some kind of proposal here.
But in the latent graph, it depends only on the observed edges.
Yeah, so the latent graph essentially, it follows this kind of proposal mask here. So if the proposal here is fully connected, then the latent graph predicts for each edge in this fully connected graph, it predicts like an output, like whether this edge should actually be there or not. Yeah, that's a very good question. So just for a few more minutes, I want to go into details in how this model works in practice. So the encoder part, you would now, if you don't know anything about the interaction structure, you would just say, okay, everything is interacting, and you run like a graph neural net on this fully connected graph here. So first, you would like to embed the observation that you have, which is like multiple time steps of dynamics, for example, and this embedding module can be a CNN, it can be an RNN, this can be anything that embeds like a certain trajectory of a particle. And in practice, we use like a CNN with some self-attentive pooling here. And then essentially you have like node embeddings which represent the trajectory of a single particle in isolation. And then you would essentially like to do some message passing on this graph, so every single node embedding in the end knows about all the other trajectories and how they all influence each other. So we first go to edge space by basically concatenating node features, feeding it through an edge update function, and then we move back into node space to inform all the nodes basically about their neighbors. And lastly, because we want to make edge predictions here for this graph, we move back into edge space and have a final output here. And just as a reminder, so these update functions look like this. You have like, if you want this node update here, you have all these edge updates that you calculated before, and then you just sum them up on the incoming node here. And in the end, we care about this latent interaction graph. So we can basically parameterize Z as a binary adjacency tensor. If you have multiple edge types, this would be like an n by n, where n is the number of nodes, by k tensor. And then we can index here Zij would be the edge type on a particular edge. And this can be a one-hot vector if you have multiple edge types. So the distribution we can choose here is basically a categorical distribution that gives us a particular edge type as an output. And it's just parameterized by a softmax of this edge output here. Now, at training time, since this is all discrete, and we have basically a discrete distribution, so we could use an EM algorithm to solve this, but we can also, on the contrary, we can basically just relax this discrete distribution into a soft distribution using what is called a concrete distribution or Gumbel softmax distribution. And that's a very simple reparameterization. Essentially, what's happening is now we just say this latent variable Z here is given by a softmax of the edge embedding plus some noise. So G is noise from a Gumbel distribution, and tau is some kind of temperature that basically tells you how how good the approximation should be. If tau is very low, if the temperature is very low, you get close to discrete distribution. If it's very high, you get close to like a uniform, kind of very soft distribution. And then you can just get gradients for this whole thing by a reparameterization trick. Basically, this just means you can just implement this in your in PyTorch, for example, and the gradients will just directly flow through the softmax function here. And the noise and the sampling procedure is all happening in this non-parameterized Gumbel distribution. And then we can put a prior also on these edges, and we explored a couple of different priors, and essentially we ended up with either choosing a uniform distribution if we don't know much about how the edge type should look like, or we can also use a sparsity-inducing prior if we just say that if whenever the model predicts the first edge type, then this means that there's no edge between two nodes. So you can hard code one edge type as no interaction, and then you can put a large weight on the prior on this like no interaction edge, and then essentially you get a sparsity-inducing prior. And then once you have this latent graph, then all we need now is basically decode the dynamics back from this latent graph. And essentially what we want to do here is we run a graph neural network on this latent graph that has to do some message passing. And of course, the dynamics have to be conditioned on some initial conditions. So basically, we start by feeding in the initial conditions, and then the graph here is given by this adjacency tensor. And for each edge types, what we found is very important. For each edge type, we have a separate message function. And then you can basically just run this model here. This is basically passing messages from nodes to edges, and then you go back from edge space to node space. And here we use what looks like a residual connection, but the idea here is basically that we predict the location difference instead of predicting the location itself. So basically it gives us like it's easier to predict location differences because it's independent of the coordinate system. And lastly, because the predictive model, we would like to predict a distribution instead of just a single point estimate. So here we choose a fixed variance, but of course you can also think about modeling this as some kind of parameterized distributions which you like to learn the parameters of. It doesn't have to be Gaussian. We explored a number of decoder variants. I'm not going to go into much detail here, but you can think of like also having a recurrent decoder that predicts multiple time steps. You can also, because a decoder directly corresponds to the same structure as a typical physics simulator, you can actually just swap out the graph neural network with a physics simulator and backpropagate through the physics simulator to train the encoder. So that's something also we've done in experiments. Or you can take a true graph, some fully connected graphs, or you can also re-estimate this graph over multiple time steps. And we tested this model on a number of sort of toy physical systems where we really know the ground truth interaction structure, where we have full control over what's going on, and where forces are getting more and more complex. So first we start with linear forces that basically only depend on the difference between node embeddings, and we just wanted to see if the graph neural net can learn these. And because we have these flexible edge update functions, MLPs basically can very easily learn this like functional form. Then we also use inverse square law forces with charged particle systems. These are a bit more difficult to learn for an MLP. And then we also looked at more complicated sinusoidal interactions. And we also found that these are actually quite easy for the model to learn. And then we applied the same model also for like some real-world data, like NBA data, which we got from the Toronto Raptors, and motion capture data. And the only table I'm going to show here now is basically that this model does, if we apply this in an unsupervised way on these data sets, then it can, without any supervision on the ground truth labels, it can discover the interaction structure. Like basically, we just sample random connections, like basically in the spring system here, we would sample springs at random, so two nodes are connected at random, and then we run the simulation, we run our model on it, and then we just see whether it has the right latent graph structure that it discovered. And we compared this with the ground truth later, and we found that basically with very high accuracy can discover these latent graphs. And even if we have a simulation-based decoder for some. We can also, the interesting thing is that it learns both this interaction structure and the dynamics at the same time. So if you look at the predictions of the dynamics, there's some interesting failure cases like this one up here, where the prediction, this blue particle here moves down and moves away from the other particles, where in the ground truth case, the blue particle moves up. And it seems like the model here sampled the wrong interaction type, but according to this wrong interaction type, it does a very reasonable kind of dynamics prediction. So to conclude, I think just to summarize like the graph neural network field in like a few sentences, I think graph neural networks recently have really come out as a model, as a very powerful class of models for data with explicit or even implicit relational or graph structure. And I think in the last 3 years or so, there has been massive growth in this research field. And it's even so massive that when I started my PhD, there were like 6 papers in this like domain like 3 years ago. And by now, the last time I checked, it's like over 1,000 papers. So there has been massive growth in the last 3 years, which is very exciting. But it's also dangerous in terms of many results are basically reinventing things that are happening in parallel. So we have to be also careful in terms of benchmarks and these kinds of things. I think what's important is to more systematically explore like the benefits of certain variants, model variants, and basically also have better benchmark data sets. And to like one big limitation that we had now in this paper here is that we always assume we have some kind of structure already given, like either we're given the complete graph, we have everything given like in these graph data sets, or here we're basically in the simulation data sets, we're given what the nodes are, but we're not given what the edges are. But the ultimate holy grail is kind of, we're just given an image like this and we would discover everything from scratch, like what is a node, what is an edge, and discover like both the objects and the relational structure from raw data. And it doesn't stop with like relational learning or relational inductive bias. I think in order to make better like improvements in terms of generalization in machine learning, I think we also should look more into things like hierarchy or compositionality and how we can build this into neural network-based models. If you're interested, I have a few more references here. Also, there's a lot of code on GitHub. We published all the code from all these papers and a few blog posts. And lastly, I want to thank my collaborators. And I think we have a few minutes for questions. Thank you.